Geometry of dynamic tetrahelix and field structures. Part 3b. The fractional harmonics within dynamic tetrahelix will be explored. Part 3b. Fractional harmonics of dynamic tetrahelix. The first harmonic of a tetrahelix that forms when the first loop is closed is the main harmonic. When the twist angle decreases further, a second loop forms, and this reveals a fractional harmonic. As the twist angle continues to decrease, additional fractional harmonics are revealed for each new loop created. For each additional lap around itself, the depth of the fractional harmonic increases by 1. M equals magnitude of the harmonic. D equals depth of the harmonic, or number of laps. M.D is the generic description. For example, 7.2 harmonic would be a harmonic with a magnitude of 7 and a depth of 2 laps. The 7.1 harmonic is the main harmonic that has a depth of 1 and is also referred as just the 7th harmonic. Example for the 7th harmonic of a loop tetrahelix. In the next video, the simulator applies a continuous twist angle scaling to a loop tetrahelix with a subsequence of 2112112, bit length equals 8, and a total length of 56 elements, which reveals the 7th harmonic patterns, 56 divided by 8. The twist angle is continuously scaled from 180 degrees to 40 degrees, and the tetrahelix transforms from a linear wave into progressively smaller loops, and the arcs overlap to form various harmonic patterns. See the table below. Eventually, as the loops get smaller, they wrap around itself and create multiple overlapping loops. Each lap around the loop reveals a different depth of the fractional harmonic for this subsequence. Starting at 180 degrees, the twist angle decreases and the tetrahelix begins to form the first loop that forms the 7.1 harmonic. The twist angle continues to decrease and closes the second loop to form the 7.2 harmonic. Then the third loop is closed to form the 7.3 harmonic. The twist angle continues to decrease and the tetrahelix then forms the fourth loop to create the 7.4 harmonic. The tetrahelix continues to wrap around itself into smaller loops until it forms the fifth loop to reveal the 7.5 harmonic. Fractional harmonics of loop tetrahelix. The same harmonic number occurs multiple times at different twist angles, but form different patterns that are called fractional harmonics. Each lap around the loop represents a fractional harmonic where each lap indicates its depth. An analogy for a fractional harmonic can be seen in a heptagon/heptagram, where it requires one or more laps around itself to connect its vertices as its interior angle decreases. For the heptagon, referred to as 7/1, its adjacent vertices are connected in one lap around its perimeter. For the heptagram, referred to as 7/2, every second vertex is connected, that takes 2 laps around its perimeter. For the heptagram, referred to as 7/3, every third vertex is connected, that takes 3 laps around its perimeter. Lower-level harmonics of loop tetrahelix. Each unique subsequence for a loop tetrahelix represents a family of harmonics. The total length of the tetrahelix determines the magnitude of the harmonic. Higher-level harmonics inherit the patterns from lower-level harmonics. This table shows the family of the 7th harmonic for this subsequence. Notice that the lower-level harmonics, 2nd to 6th, show up in this table. The green rows show the different depths of the 7th harmonic. This corresponds to the twist angle where the oldest and youngest elements align to create a closed loop. The white rows show the lower-level harmonics, which have a length less than 56. As a result, these patterns do not form a closed loop because the extra elements force the oldest and youngest element to be misaligned. This video reveals the lower-level harmonics found between the 7.1 and 7.2 harmonics. This is the 7.1 harmonic. As the twist angle decreases further, it reveals the 6.1 harmonic. The twist angle continues decreasing, and then reveals the 5.1 harmonic. The twist angle decreases further and then reveals the 4.1 harmonic. Then we reach the 7.2 harmonic. Higher-level harmonics. Higher-level harmonics can be introduced by increasing the total length of the tetrahelix. This table shows only a portion of harmonics that occur as the total length is increased from 56 to 160 elements, which reveals the 20th harmonic, 160 divided by 8. The next video illustrates some of the patterns of the 20th harmonic. 20th harmonic and accumulation of motion. This video reveals the patterns of the 20th harmonic for this subsequence. Here's the 19th harmonic. Here's the 14th harmonic. Here's the 9th harmonic. Here's the 13th harmonic. Here's the 17th harmonic. Here's the 4th harmonic. The 7th harmonic and 20th reside on the same curvature of space, which is determined by the subsequence of the tetrahelix. The longer length also creates more accumulation of motion in the younger elements, and they move faster than the elements did for the 7th harmonic. An analogy to this is the motion of a bullwhip. Bullwhip. Sections of the whip further away from the handle move faster than those closer to the handle. Plot of twist angle versus harmonic number. This plot reveals various trend lines and groupings for the 20th harmonic of subsequence 211211212. This includes the harmonics for magnitudes between the 2nd harmonic and the 20th harmonic and the corresponding twist angle. The twist angle is shown on the x-axis, and the harmonic magnitude is shown on the y-axis. Let's look at some of the groupings. The red dashed line represents all the 7th harmonics of different depths, which can be represented as 7.d. These highlighted trend lines group together all of the harmonics in this family based on their depth. This first trend line groups the main harmonics created in the first lap that have a depth of 1, indicated by m.1, for example, 2.1, 3.1, 4.1, etc. The second trend line groups the fractional harmonics that have a depth of 2, indicated by m.2, as an example, 3.2, 4.2, 5.2, etc. Trend lines for m.3 and m.4 have also been highlighted. This vertical group shows all the harmonics that have the same pattern as the main 2nd harmonic and can be represented as m divided by d equals 2. The higher magnitude harmonics, which have a longer length, require more laps, and have more depth, and these extra loops overlap perfectly and result in the same pattern seen for the 2nd harmonic. This next grouping shows the magnitude of the harmonic increasing by 1, as well as the depth of the harmonic increasing by 1 for each data point. This trend line shows a group of increasing, odd-numbered harmonics, where the depth of the harmonic also increases by 1 for each data point. Part 3b wrap up. This concludes Part 3b of the presentation on the harmonics of dynamic tetrahelix. In Part 4 of the presentation, the core field structure, CFS, which is a unique tetrahelix, will be examined as a model for field structures, and the modified tetrahelix system will be introduced.